Now we're starting your transistor. Okay. So basically there are two types of transistor. One is called BJT. Okay. One is called FATs. Okay. BJT is your bipolar junction transistor. Bipolar junction transistor. And FAT is your field effect transistor. Field effect. Field effect transistor. Now, as name suggests, okay, this is the field control device. Okay, field control device, and here this is your current control device. So the name is bipolar. Okay, why the name is bipolar? Because in BJT you need both charges, majority as well minority charge carriers, and both hole or electron. You need both type of carriers to explain the operation of transistor. Okay, so I can write here both electron hole or majority charge carriers as well as minority charge carriers are required, okay, for operation. Okay. And BJTs are basically current control devices. Okay. The second point you can mention difference. These are current controlled devices. Okay. While your FET is field effect transistor. Okay. So they are unipolar. Okay. So only these are field control devices. Okay. Field controls. Okay. And field only controls majority charge carriers. Okay. So field controls majority charge carriers. This is the basically difference between two transistor. Okay, so let us first take bipolar junction transistor in detail. So BJT, let me give the construction of BJT. So I'm erasing this one. Okay, so this is your BJT. Okay, so BJT has a three layers. You have a N, or you can write first P and P. Okay, so this is P and P. So it is at three terminals. Okay, one is your emitter, other is your base, and this is your collector. Okay. Similarly, we have also NPN transistor also. So where emitter is N, your base is P type, and your collector is N type. Okay. So it has a three layers. Okay. Okay. Forming two junctions. Okay. So one is emitter base, and this is a collector base. So we have two junctions here. Okay. So two junctions. So one junction is called your EB junction, emitter base junction, and other is your base emitter junction, base collector junction, or CB junction or BC junction, whatever you want to say, CB junction. Now, obviously, there is some barrier is there. So let me first draw this some small PN junction barrier is there. Okay. Now, what are the characteristics of these layers? Okay. So these layers are not uniform. They are not similar kind of course there's a p type, is n type, is p type. Okay, but other than this, their size also not different. Size is also different. Okay, their size difference plus there's a doping difference. So if your ammeter, if you take your ammeter, okay, ammeter. So ammeter is highly doped. Ammeter section is highly doped. Ammeter is highly doped. Doping ज़्यादा है. If you want, you can write here P plus also. Okay, high doping means it is high doping. And where you take your base, okay, so base doping is very less. Base doping is low. Doping is low. Okay, doping is low. Now collector doping, you can say it is moderate doping. Okay, moderate doping. Okay, so some book says that collector has a lowest doping. Okay, but I keep like this only because base doping should be low. That is requirement. Okay, because we want very less recombination here. So that is, so then you should remember that ammeter is a highly doped. In doping, your ammeter is very highly doped. Okay, and thus if I talk about the cross section area, this is my junction. Okay, this is my transistor. One junction, one layer is a second layer, third layer. Okay, so they have cross section. Okay, so cross section wise, collector is very large. Okay, so cross section, so collector cross section is highest. So collector cross section is high. Okay, compared to other junctions, or you can write compared to ammeter. Okay, so now this is the basically design. And if I talk the most important parameter in this design, that is thickness of base. Okay, so base thickness. So base thickness is only 5 micrometer. Okay, and this is very important thing because this only differentiate this three layer transistor from a two PN junctions. Okay, here we have two junctions. Okay, PN junction, LP junction. So instead of using this NP one three layer, we can use two diode. Okay, but that connection will have a different characteristics. Okay, than this one, because here the base is very thin. Okay, so base is very thin. So what happens if you inject a charge carriers here, the charge carriers can move from here to here. Okay, so this is a very critical parameter of design of your transistor, very important parameter, and this is the reason why transistor behaves differently than than comparison to two diode. Okay, connected back to back. So now if we want to understand the operation of this NPN junction, okay, so this or NPN or PNP junction, so these junction first has to be biased. Okay, so for example, if I take this PNP junction first, and then we'll talk about NPN junction. Okay, how it works. So if I apply, suppose this ammeter, so they can work in three configuration. Okay, one is called common base configuration. Common base configuration. Okay. Second is your common ammeter configuration, and your third is your common collector junction configuration. Common collector configuration. So out of three terminals, one has to be grounded. Okay, and with respect to that ground, we have to apply voltage to other two junctions. Okay, so now we have two junctions, and that two junction we have to give biasing. Okay, so that biasing can be four type. Suppose I'm making this junction first common base configuration. Okay, so I'm making this base common first. Okay, so base is common, grounded. Okay, now I want to apply biasing. So what I can do this junction forward bias, I can do this reverse bias, I can do this forward reverse bias, this forward bias. Okay, this forward, this reverse, this reverse. Okay, so there are basically 4 type of biasing we can apply. Now you know what is the forward bias. Forward bias means what? What do you mean by forward bias?
P part higher potential पर N part lower potential.
Okay, yes, so we have a junctions. We have one emitter based junction, and then we have a collector based junction. We have 2 junctions. Okay, so here this is the one junction EB, and this is your CB or BC. Okay, so I can apply 2 type of biasing. I can apply this is forward bias, okay, forward bias VB, and this is your reverse bias, okay, which is the usual type of biasing. Okay, and when you apply this type of biasing, the operation region of transistor is called active region. Okay, we'll discuss what is this active region. So transistor is called to be working in active when you have forward bias, reverse bias. Okay, and this type of biasing is basically used for your amplifier. Okay, and the second is your called your, this is also forward bias, this is also forward bias. Okay, so the operation region will be your saturation. Okay, third is your reverse bias, the operation region will be cutoff. Okay, and the last is inverse of this one. This is reverse bias and this is forward bias. Okay, that is called inverse operation. Okay, that is rarely used. That is that. Okay, so when you apply reverse bias, forward bias, तो क्या हो जाएगा, ये आपका अमीटर बन जाएगा. अगर उल्टा कर रहे हो, यहाँ से करंट इंजेक्ट करा रहे हो, तो उल्टा कर दोगे तो यहाँ से ये आपका क्या बन जाएगा, ये फॉरवर्ड बायस है, तो यहाँ से करंट इंजेक्ट होगा, तो ये आपका अमीटर बन जाएगा, पर इसका डोपिंग तो बहुत कम है. That has no use. Okay, we don't use. That is called your inverse operation. So this type of biasing is not used. So ये यूज होती है एम्पलीफायर के अंदर, ये यूज होती है आपकी when transistor work as a switch. Okay, so this is for amplifier. This is for switch. Okay, and this we rarely use. Okay, now let us understand what do you mean by this forward bias, reverse bias का मतलब क्या है और उससे क्या फर्क पड़ता है डिवाइस पे, डिवाइस की कैरेक्टरिस्टिक कैसे आती है. नाउ दोस वी हैव टू डिस्कस. तो इसको रब कर दूं मैं. ओके,
यस सर.
सो ये चारों बायसिंग को पहले समझना है, और ये जो ऑपरेशन रीजन मैंने लिखे हैं यही ट्रांजिस्टर का फंडामेंटल है. इफ यू अंडरस्टैंड द बायसिंग एंड अंडरस्टैंड द ऑपरेशन रीजन, ओके, देन ट्रांजिस्टर इज डन. ट्रांजिस्टर के सर्किट बहुत आसान होते हैं सॉल्व करना. ओके, सो आई एम फर्स्ट स्टार्टिंग विद अ कॉमन बेस कॉन्फ़िगरेशन. ओके, कॉमन बेस कॉन्फ़िगरेशन. सो कॉमन बेस कॉन्फ़िगरेशन पे क्या होता है, you apply your base is common. Okay, let me draw a longer one. Your base is common. Okay, and you're applying voltage between ammeter and base. Okay, so since I'm applying, this is a grounded and this is a V, so I'm writing this is a battery name as a VE. Okay, this battery is VE. Okay, here you're applying VE. Okay, so this is forward bias. Okay, so this is the usual biasing. This should be forward bias and this should be reverse bias. Okay, now this is a PNP. So if I want to make forward bias, the positive of the battery should be connected to P. Now similarly, this is PNP, this is also P. I want to make it reverse bias. So what I'll do, this will be minus plus minus plus. Okay, and I'm connecting this as a, I'm calling it as a VCC. Okay, so now this junction become first junction is forward bias, other junction is your reverse bias. Okay, now how the operation take place? Now what happens, because when you apply voltage, this junction is forward bias and the voltage drop across this will be, okay, VEB. Okay, if it is PNP, the voltage drop, this will be your VEB. Okay, and the voltage drop between base, okay, base and collector, that will be your VCB. B common hai, so the voltage of VC with respect to B, the voltage drop will be VCB. Okay, and if I connect the voltage of this one, that is called VCE. Okay, VCE. VCE is the voltage between ammeter and collector, and if you see VCE in the circuit, so VCE is equal to your VEB or VEB in PNP, and in NPN it will be VBE. Okay, this is VEB plus VCB. So this is a very important relation. You have to remember this relation. Okay, we'll talk about this. Okay, so this VEB VCB is equal to your VCE. This is common base configuration. Now, as soon as I apply forward bias, what will happen? This much voltage will develop, or whenever you are in junction, if you allow the voltage, okay, if you apply some voltage, what will happen? Current will flow. Yes or no? Okay. So now here also, when I apply voltage, the current flows. Okay. So the current, okay, this current is called IE, because it is going here. So this current I call it IE. Okay, ammeter current. So ammeter current is going here. Okay, coming here. Now this current means your electrons are coming this side. Okay, if you have plus battery, you are pulling electron here. Your holes are moving like this. Now, if these holes move here, so let me draw here. Okay, so your holes are moving here. So this is P, this is N side, this is P. Okay, so your holes are moving like this. They are forming a current IE. Now here you have electrons. In base regions, you have electrons. Okay, now what will happen when you apply forward bias? Some of these holes, okay, or you say holes are moving, or you say electrons are moving this side, the same thing. Okay, so what will happen? This hole and electron will combine. They'll recombine here. So as they recombine here यहाँ पे क्या हो जाएंगे? इलेक्ट्रॉन कम हो जाएंगे. अब इलेक्ट्रॉन कम हो जाएंगे तो वो इलेक्ट्रॉन कहां से आएंगे? बताओ, सर्किट कैसे पूरा होता है? कलेक्टर से कहां से आएंगे? अगर यहाँ अभी वोल्टेज तो यही लगा रहे हैं, बेस से आएंगे, तो इलेक्ट्रॉन कहां से? इलेक्ट्रॉन ऊपर जाएंगे तो करंट कहां जाएगा? नीचे. तो ये करंट विल फॉर्म IB and IB. So I is basically called your ammeter current. Ammeter current. Okay, and your IB is called base current. इसको बेस करंट बोल दो या इसको बोल दो रिकॉम्बिनेशन करंट. ये आपका है रिकॉम्बिनेशन करंट. अब इसका समरी बहुत आसान है क्वेश्चन लगाने के लिए, पर मैं थोड़ा बेसिक बता रहा हूँ. तो दिस इज योर रिकॉम्बिनेशन करंट. ओके, सो यहाँ पे जितने भी इलेक्ट्रॉन लूज होंगे वो यहाँ से आएंगे और करंट बन जाएगी इधर. अब जो यहाँ पे कुछ पोर्शन जो IE का यहाँ पे रिकम्बाइन हो गया, बाकी जाके कहाँ बनेगा? बाकी जाके आपको बनाएगी IC. बाकी करंट जो होगी आपकी IC. ओके, अब यहाँ पे क्या हुआ है? यहाँ पे इलेक्ट्रॉन नेगेटिव चार्ज है, यहाँ रिवर्स बायस है. तो रिवर्स बायस क्या कर रहा है? रिवर्स बायस क्या कर रहा है? एक तो इलेक्ट्रॉन को पुल कर रहा है, और या अपोजिट सेंस में समझे तो इलेक्ट्रॉन को क्या कर रहा है? कैप्चर कर रहा है, होल को कैप्चर कर रहा है यहाँ पे. ओके, तो यहाँ से होल आ रहे हैं और इस बैटरी से हम उसको जितने भी जंक्शन पे जितने भी है उनको स्वैप कर रहे हैं, तो उससे करंट IC बन रहा है. अब कुछ लॉस हो जा रहा है, IE कुछ यहाँ से रिकम्बाइन हो जा रहा है, तो पूरा का पूरा IE यहाँ नहीं पहुंच रहा है, IC पहुंच रहा है. लेकिन IE और IC दोनों बराबर ही होते हैं. ओके, यस.
Can you please explain in English, sir?
I'm telling, we are applying here forward bias. Okay, this forward bias will generate a current, forward current, IE ammeter current. Okay, now this ammeter current is passing through this region, N region. Here electrons are present. That so that some of the holes will recombine with this electron, because this is a n doping. Here more, here electrons are more compared to holes. Okay, and doping is low, so electron also less. Okay, so this is highly doped, so there are many holes. The holes are going here, with some holes recombine with the electron, so that will reduce the number of electron here. Those number of electron will come from here. Electron will come from base. Okay, the base current will go down, and the remaining current will reach here. Okay, which is swept by this battery. So this battery is pulling all the holes. Okay, you can understand this way. So now, if we see this junction, so this is a forward bias junction. Here you are getting forward current, and this is your reverse bias junction. So here also you should get reverse saturation current. Yes or no? So if I say my IE coming here, okay, this is my junction. Okay, so
सर
1 minute, 1 minute. हाँ, बोलिए.
सर आई करंट पी से एन जा रहा है ना, तो
आई, हाँ हाँ
हाँ पी रीजन से एन रीजन जा रहा है,
हाँ,
तो एन में से इलेक्ट्रॉन बढ़ेंगे ना, वो करंट जा रहा है.
होल करंट है ना, इलेक्ट्रॉन तो खींच रहा है. समझ, उल्टा समझो इसको. होल जा रहा है मतलब इलेक्ट्रॉन आ रहा है. ओके, तो इलेक्ट्रॉन कम हो रहा है यहाँ पर. समझ लो कि ये इलेक्ट्रॉन यहाँ से जा रहा है, और ये इलेक्ट्रॉन यहाँ से आ रहा है और इधर जा रहा है, और यहाँ होल से कंबाइन हो रहा है. सब उसको उल्टा समझो. और क्योंकि हम करंट को ऐसे लेते हैं, होल्स को हम बोल रहे हैं होल्स इधर जा रहा है और यहाँ पे इलेक्ट्रॉन को कम कर रहा है.
तो ये कन्वेंशनल करंट है इसके वजह से क्या?
हाँ, कन्वेंशन करंट है. वैसे तो करंट इलेक्ट्रॉन से होती है, पर कन्वेंशन करंट की डायरेक्शन तो हमेशा हम ऐसे ही लेते हैं ना, हमेशा एक्सप्लेन करते समय तो हम ऐसे ही बताते हैं.
ओके, मुझे ओके.
सर
तो
बेस से इलेक्ट्रॉन्स जा रहे हैं, मतलब बेस ग्राउंडेड है इसलिए इलेक्ट्रॉन्स ऊपर जा पा रहे हैं.
बैटरी लगा रहे हो ना भी, किसी भी सैंपल पे आप लगाते हो, कोई भी चीज के लगाते हो, वोल्टेज करंट कैसे फ्लो होता है? आप
वोल्टेज के
करंट
कारण.
करंट फ्लो कर रहे हो ना, वैसे ही आप दो जंक्शन पे लगा रहे हो तो इस पे करंट फ्लो कर रहे हो. ओके,
यस सर.
सो ये आई यहाँ पर है, आईसी यहाँ पहुंच गया. ओके, इसमें से, और आपका क्या आई बी आपके नीचे चला गया. सो से अल्फा पार्ट ऑफ, सो से दिस इज आई, एंड अल्फा पोर्शन ऑफ IE makes IC. Okay, so let me call this I is current is coming, alpha I is reaching here. Okay, and 1 minus alpha I is going to the base where alpha is close to 1. Okay, so this is because of forward biasing. Now यहाँ पर reverse biasing है. Reverse biasing करंट क्या होगा? एक करंट फ्लो होता है अगर डायोड रिवर्स बायस है, अगर जंक्शन रिवर्स बायस है. ओके, NP, और यहाँ आप वोल्टेज लगा रहे हो, तो इसमें से भी करंट फ्लो होता है. उसको क्या बोलते हैं? रिवर्स सैचुरेशन करंट. यस और नो? इफ आई अप्लाई reverse bias to a diode, then also current will flow. Okay, that current is called reverse saturation current. Okay, so I call that current as a ICBO. Okay, this is reverse saturation current. Okay, base is common, so this is called a reverse saturation current will flow because of this negative battery here. So now if I write the equation for current relation for common base junction.
Sir,
हाँ,
so this base current and ICBO is same thing,
नो
है ना?
ये तो रिवर्स सैचुरेशन करंट है. ये करंट जो आ रही है ये तो रिकॉम्बिनेशन करंट है. ये
Yes,
ये बाहर निकल रही है, और इसके
yes.
कारण जो करंट जा रहा है वो अंदर जा रहा है. तभी तो उल्टा है.
Okay, that IC is taken as that reverse saturation current.
हाँ, which is ICBO. अभी
सर
बताया ना.
ये लीकेज करंट होगा ना.
जंक्शन क्या है? ये जंक्शन रिवर्स बायस है कि नहीं है?
Yes, sir.
तो इसमें भी करंट फ्लो करेगा ना, रिवर्स के कारण. आप रिवर्स बायस लगा रहे हो यहाँ पर, यहाँ प्लस लगा रहे हो, तो इसमें भी तो करंट फ्लो करेगा एक.
ठीक है. इनसाइड जो जंक्शन के इनसाइड है वो ICBO है, और जो आउटसाइड करंट आ रहा है वो कलेक्टर करंट है.
अभी बता रहा हूँ. अभी एक करंट यहाँ आई आ रहा है, और उसका अल्फा पोर्शन यहाँ पे रीच कर रहा है. ठीक है,
यस सर. ओके,
होल्स आ रहे हैं, 100 में से 99 होल यहाँ पहुंच रहे हैं. एक होल,
ठीक है सर.
एक इलेक्ट्रॉन नीचे चला गया, या होल नीचे चला गया.
ठीक है
ठीक है,
सर.
और यहाँ पे रिवर्स बायस लगा रहे हैं, इसके कारण भी रिवर्स बायस करंट फ्लो हो रहा है. ठीक है, दो चीजें हो रही हैं. तो अब ये जो कलेक्टर पे करंट फ्लो हो रहा है, दैट विल फॉर्म IC. तो मेरा अब IC क्या हो जाएगा? माई IC विल बी what? IC will be my alpha IE or plus ICBO.
Yes, sir.
This
Yes.
this is the IC equation for IC. Similarly, if I want to write my IB, मेरा IB क्या होगा बताओ? 1 minus alpha IE minus ICBO. Yes or no? बताओ. IB. So this is my IB. These two components from IB. रिजल्टेंट करंट क्या है? आई यहाँ से आया, अल्फा यहाँ चला गया, यहाँ से आईसी भी आया, तो आई अल्फा आई प्लस आईसी भी फॉर्म आईसी करंट. ओके, नाउ रिजल्टेंट करंट इज आईबी. ओके, आउट ऑफ आईबी दिस करंट इज coming outside and this is going in, this going in. So this, the difference of this one is your IB. Okay, so this is your IB. Now if you sum these two things, this will give you what? IC plus IB equals to what? IE. Any question, Parampreet?
Clear, sir.
क्या ये क्लियर है कि नहीं बताओ?
सर प्लीज जरा आईबी का एक्सप्रेशन एक बार बताओगे?
अरे यहाँ पे दिख नहीं रहा है तुमको? आईबी क्या है? फाइनल करंट, रिजल्टेंट करंट आईबी है. तो उसमें वो किससे बनी हुई है? अल्फा चला गया इधर, 1 माइनस अल्फा 99 चला गया, 1 अल्फा चला गया, 1 माइनस अल्फा नीचे आया आई का, एक करंट ये बन गया. और इस जंक्शन पे एक करंट उल्टा भी फ्लो कर रहा है. तो जैसे मैंने आईसी बोला है, आईसी इक्वल टू अल्फा ई, और ये करंट दोनों जुड़ गए हैं, तो ये करंट जुड़ा है, तो आईबी में ये करंट माइनस नहीं होगा क्या?
यस सर, क्लियर, थैंक
यहाँ पे
यू.
जोड़ा क्यों फिर? और यहाँ माइनस नहीं कर सकते, यहाँ पे क्यों जोड़ा फिर? ओके, सो सर्किट में दिस इज वन करंट इज रिवर्स सैचुरेशन करंट. ओके, और एक दूसरा करंट आ रहा है, वहां से इंजेक्ट हो रहा है इलेक्ट्रॉन, तो ये दोनों जुड़ के आईसी बना रहा है. और यहाँ से इलेक्ट्रॉन कम हो रहा है तो ये जा रहा है, तो ये करंट बना रहा है, और इस टर्मिनल से ये करंट यहाँ उल्टा जा रहा है. रिजल्टेंट करंट क्या जा रहा है? आईबी. इन दोनों का रिजल्टेंट भी तो आईबी आएगा. ये जो अल्फा है, ये जो है, और इसका जो इन दोनों का रिजल्टेंट तो आईबी आएगा. ओके, so this is your IB. Okay, now you sum this one. So this is called your main equation, fundamental equation of transistor. Okay, so your IE is equals to IC plus IB. This is your transistor equation, transistor current equation. Okay, now what is alpha? Okay, so alpha is current gain, common base current gain. Okay, so now let me write what is your alpha. Okay. So this is the common base configuration, and common base configuration, your current gain, okay, is written by alpha. And alpha की वैल्यू क्या आएगी यहाँ से बताओ? अल्फा की वैल्यू आएगी यहाँ से
IC upon IE.
IC माइनस ICBO अपॉन IE. ओके, अब क्योंकि ICBO इज वेरी वेरी लेस, रिवर्स सैचुरेशन करंट है, तो ये तो एग्जैक्ट फॉर्मूला है. तो यू कैन आल्सो राइट अल्फा इक्वल टू योर IC अपॉन IE. ओके, करंट गेन मतलब आउटपुट पे कितना करंट है, इनपुट पे कितना करंट है. अब वो गेन है कि कम हो रहा है, रेशियो इज वी कॉल्ड IC by IE, and this ratio is almost equal to what? This ratio is, so alpha is generally given values. Okay, so 0.8 to 0.999, you can say 98, वो तो vary करता रहता है. Okay, so question में दे रखा होगा what is alpha value, so that means your alpha is close to 1. You can write alpha value is close to 1 because these two currents are almost same. This IB is very negligible. So when IB is negligible, the whole IE is forming IC. So we generally in circuit we take IE equals to IC. जब भी हम whenever we'll solve the circuit, we'll take most of the times we'll take IE equal to IC because IB is very very negligible. Okay, so this is the one thing. Now same thing I can do for NPN transistor. Okay, now if I do same thing for NPN transistor, the working is exactly same, only the polarities will change. If I do this NPN transistor, this will be N, this will be P, this will be N. Okay, you are making base ground, you have N, minus plus plus. Okay, this is your emitter base and this is your collector, and it should be reverse bias. So reverse bias, it should be positive. Okay, this is now become my VCC. Okay, and now this time my VCB will be like this. Okay, this will be VCB, and this will be now what? Minus plus. This will be now VBE. This is plus, this is minus. So if I go from here to here, this will be VBE. This will be VBE. पहले क्या था? This is this plus, this is a minus. This is VEB. Okay, and similarly, this is minus, this is plus. Okay, so the meaning is same, only the sign change. Okay, drop will be same. Okay, so you can, if you want, you can call it now VBC, because you're making, this is ground, na? That means, so this is ground. That's why we're writing this VBC. Okay, this C, or let me write VCB only. Okay, or if you want, you can write VBC also. Okay, so VEB and VB are same, both are same. Okay, on a sign difference. If you're going calculating VBE, that is 0.7. If you're calculating VEB, that is minus 0.7. Okay, now here what will happen? Here when you apply forward bias, तो अब क्या होगा? यहाँ पे electron, you are applying negative here. So what will happen? The current will come in or current will come out? What will be the direction of current? Tell me. What will be the direction of current?
Inside.
Inside तो पहले भी था.
Outside.
Now
outside, outside.
it's electrons, na? Now you're pushing electrons. So electrons are moving like this. Earlier you are pulling the electrons, so current is going like this. Now you are pushing the electrons, so current is, so IE come out. Okay. So IE come out, and so IE coming out, that means your IB will also go inside. IB will go inside, and similarly, what will happen? This one, your IC will also go inside. The relations are same. Okay, but now because the biasings are different, so the current direction will change. Okay, now अगर मुझे PNP transistor, this is my PNP transistor. If I want to do transistor, okay, so this is, say this is ammeter, say this is collector, say this is base. Okay, so if this is a PNP transistor, so current always goes from P to N. Okay, so current will go inside here in PNP junction. This is a symbol of PNP transistor. Okay. Similarly, if you have here this one, okay, this one, okay. If it is an NPN transistor, so this is the P and P part. Okay, NPN, this is your N, this is P, this is N. Okay, so current always goes from what? P to N. So current will go from NPN. Current will go outside. Just 1 minute. Okay, so current goes P to N. Okay, so current will be going outside. This is ammeter. This is ammeter. This is a base. This is a collector. Okay, so this is symbol for your NPN transistor. हाँ, अभी इसमें कुछ डाउट है तो पूछो.
सर पीएनपी वाले डायग्राम में
हाँ.
ऊपर VEC होगा क्या? VCE को अपन VEC लिखेंगे?
हाँ, ऐसा लिख सकते हो. VEC लिख सकते हो आप. वोल्टेज ऑफ E विथ रिस्पेक्ट टू C, VEC लिख सकते हो आप. ठीक है, पर वैल्यू सेम ही आएगी ना. वो तो हम जो ट्रांजिशन लेंगे उसका ये VEC आएगा तो NPN में VC हो जाएगा.
यस सर.
Okay, NPN में VC हो जाएगा वो. So let me write VEC. What is now?
Sir, here NPN transistor, second one में a current will flow in outward, outside, sir.
Yes.
Then electrons will move in.
Electrons are moving inside because your electrons are there. Na? This is your repelling. This is a battery. You are repelling the electrons. So electron will go inside. Current will come outside. Here, what you getting? You are pulling the electron plus battery. P junction. You are pulling the electron, attract the electron. So holes moving. So current going inside. So exactly opposite is there. Okay.
Yes, sir.
Now,
Got it, sir.
now हमको एक्चुअली करना क्या है, हमारे लिए सबसे इम्पोर्टेंट चीज क्या है इस ट्रांजिस्टर में समझने के लिए. Okay, so I am taking now example of NPN transistor. Okay, so if I want to solve the problems and understand the working of junction, अब जो important thing है वो समझ लो क्या होता है. Okay, so there are two type of characteristics. One is called your input characteristics. And second is called your output characteristics. Output characteristics. Okay. Input characteristic क्या होती है? Input में क्या करेंगे आप लोग कि you will plot graph between input voltage and input current. Okay. So I'm using this common base configuration. Okay. So this is graph of input. तो input current क्या है? बताओ. Input current क्या है common base में?
IE, sir.
IE, very good. So graph between IE versus input voltage क्या है? Input voltage क्या है?
VEB.
VEB. Okay, if it is a NPN transistor, this is VB. You write VB, your V, it's the same thing. Okay, keeping the output voltage constant. Output voltage is what? In common base, what is output voltage?
VCB.
VCB. So with the plot between IE versus VB, keeping, okay, this plot IE versus VB, keeping VCB constant. This is called your input characteristics. Okay, and the plot, okay, between output current is what? IC versus output voltage VCB, keeping input current is IE constant, okay, VCB constant. Those graph is called your output characteristics. Okay, सर्किट में जो हम we have called here, हमने जो बनाया अभी जो हमने पीएन जंक्शन बनाया था, N P N, okay, I'm drawing now for NPN. So you are applying here VB. Okay, here you have this is grounded. Here you have a VCB, and this is your VCE. Okay, now what you're doing, you are up. इसका mic on है. So you are changing VB now in order to current conduction के लिए क्या चाहिए? You need some voltage. Okay, so this current will start from here. Okay, this is your VB. Okay, and this is your IE. So this is your input graph. So now I'm keeping VCB constant. So suppose मैंने VCB को 1 volt रख दिया, VCB become 1 volt. Okay, now this value is generally 0.7 volt. So यही आपको मेनली समझना है कि VB जो हमारे यहाँ पे ड्रॉप हो रहा है, okay, that is value 0.7 for solving the transistor. Okay, now keeping VCB constant. Okay, now suppose if I increase the value of VCB, if increase this biasing, what will happen? Now what will happen? This VEB will be almost same, but your current will change. Suppose I'm applying VCB equals to now 2 volt. Similarly, if I apply VCB 3 volts, okay, then this will be almost same. You can say slightly VB is decreasing. Now this type of understanding is not required for the problems. Okay, but if I'm just explaining the actual graph, when you plot in the laboratory, they comes like this. If you increase the VCB, okay, this VB slightly decreases. Okay, VB slightly decreases means what? You are getting higher current IE for lesser voltage. Okay, now try to understand what happening. So whenever I apply VCB here, so VCB is a reverse bias. So now in between your N and P, N and P, and N and N, there's a P. So here junction is there. So whenever you apply reverse bias, so reverse bias, what will happen? The depletion layer width will increase. So if depletion layer width increases, your base becomes smaller. And once base becomes smaller, now the probability of recombination decreases, because ultimately your I is coming here, and that your I is making IC. If this base becomes smaller, width becomes smaller, यहाँ पे तो इलेक्ट्रिक फील्ड है, जो डिप्लेशन लेयर है वहां पे इलेक्ट्रिक फील्ड है, जैसे ही वहां इलेक्ट्रॉन पहुंचेंगे that will be captured by the battery. So if this width decreases, so automatically the probability of recombination decreases, so your IC increases, your IE reaches more and more IE reaches here. Okay, so or in reverse you can say, if this depletion layer decreases, so your recombination is taking less, that means IB decreasing. Okay, IB decreasing and the capture is more. Okay, so that means you are making more current to flow, or more, either you say more current to flow, or you say the applying reverse bias is equal, higher reverse bias is equivalent to increasing the forward bias here. क्योंकि जब यहाँ पे रिवर्स बायस लगाओगे, ये प्लस है, इसको आप यू आर मेकिंग इट मोर नेगेटिव. So when you are making it more negative, automatically this become more positive. इसको इस तरह अंडरस्टैंड करो. If you are applying reverse bias here, you are making this is more positive, this is more negative. Okay, if it is more negative, then automatically this become more forward bias. So now if you increase the VCB, okay, for lesser voltage you get same current. You are getting same current here for 3 volt. Okay, what current you are getting here for 1 volt, same current you are getting here for 3 volt, but your forward bias voltage decreases. So lesser VBE, you are getting same current IE. So why? Because now your IB decreases. So I can call it base width modulation. Base width modulation. Okay. Now what is base width modulation effect? Okay. So increasing reverse bias, when you increase the reverse bias, okay, so you say you increase the VCB, okay, what happens? It decreases depletion layer width. Okay, so depletion layer width, okay, at CB junction increases, and when this increases, base width decreases, and base width decreases, recombination decreases. Okay, so what happens? Base width recombination decreases. Okay, recombination decreases means your IB decreases. Okay, so here more IC is coming. So more IC is coming. In opposite sense, you can say the I is increasing. Okay, your I is your I is increasing. You can call it like this. Okay, so because now for this voltage you have this current. Now same voltage you have a higher, so you will be giving higher current, higher IE. Okay, same VBE. Either you say IE is increasing or you say VB decreasing. Both are same thing, because ultimately VB बढ़ाने से ही आपका IE बढ़ता है. तो या तो बोलो कि सेम वोल्टेज VB आपने सेम रख दिया तो आपका IE बढ़ गया. If you reduce the you keep the current same, then you can say my VB decreasing, but it is very slightly change. Okay, so more the VCB, more the better collection of charge carriers. Okay, अब ये सब प्रॉब्लम सॉल्व करने के लिए जरूरी नहीं है. प्रॉब्लम सॉल्व करने के लिए ओनली आपको द मोस्ट इंपॉर्टेंट पैरामीटर व्हाट यू हैव टू रिमेंबर, दैट इज योर VB वैल्यू इज 0.7. दैट्स इट. इस ग्राफ का जो पर्पस है बताने का, इनपुट कैरेक्टरिस्टिक, वो यही है कि आपका VB जो जब भी ट्रांजिस्टर में ड्रॉप होगा बेस एमिटर जंक्शन पे, दैट वैल्यू विल बी 0.7. दिस इज वन थिंग. ओके, तो ये दिस पॉइंट यू टू रिमेंबर. एंड द नेक्स्ट इज आउटपुट कैरेक्टरिस्टिक्स. Now, what is output characteristics? How much time is remaining? Have I finished my time? Okay, so let us discuss this tomorrow because it's taking more time. Okay, so I'll discuss it tomorrow. तो मेनली हमको ट्रांजिस्टर समझने के लिए क्या करना है, हमको इसकी इनपुट एंड आउटपुट कैरेक्टरिस्टिक्स समझनी है. ओके, और वो भी हम इसलिए हमको कॉमन एमीटर कॉन्फ़िगरेशन में करना है. तो कल हम इसको फिनिश करेंगे. पहले कॉमन बेस एमीटर में इनपुट और आउटपुट करेंगे, वो एक फंडामेंटल है, क्योंकि कॉमन अमीटर पढ़ा रहे हैं, जिससे पहले कॉमन बेस पढ़ा रहे हैं। तो हमारे लिए जो इम्पोर्टेंट है एग्जाम के लिए, क्योंकि कॉमन अमीटर कॉन्फ़िगरेशन ही यूज होता है मेनली आपके एम्पलीफायर के लिए, तो हमको मेनली उसी को डिस्कस करना है। उसी के सारे जो साइन है, बायसिंग के साइन है, उसको अंडरस्टैंड करना है। उसी से हमको समझना है कि ट्रांजिस्टर कब जाएगा एक्टिव रीजन में, कब जाएगा कट ऑफ रीजन में, कब जाएगा सैचुरेशन रीजन में। ओके, तो दैट वी विल डिस्कस टुमारो। ओके
सर 6:55 तक है ना
क्लास इज
आज क्लास?
मेरी 5:45 से है ना, 5:45 टू हाउ मच टाइम?
6:55 तक है सर आपकी।
ओके ओके ओके
सर
हाँ बोलिए। तो ठीक है, टाइम वेस्ट करते हैं, लेट अस कंटिन्यू।
सर एक छोटा सा डाउट था सर।
हाँ
जैसे सर्किट में हम लोग ये कोशिश कर रहे हैं कि मैक्सिमम करंट आउटपुट में आदमी ले सके,
हाँ
तो सर ये ट्रांजिस्टर मतलब लगा क्यों रहे? डायरेक्ट इसको हटा के डायरेक्ट करंट ही ले लेते हैं।
हाँ, तो फिर तुम्हारा फिर तुम्हारा एप्लीकेशन कैसे बनेगा? अभी तुम जैसे डायोड बनाते हो, ठीक है,
यस सर।
तो डायोड को क्यों यूज करते हो? रेक्टिफायर के लिए ना।
यस
अब तो
सर।
फिर तो कुछ एप्लीकेशन तभी तो यूज कर रहे हो,
ओ
ठीक है। और यहाँ पे भी कुछ एप्लीकेशन तभी तो कर रहे हो। यहाँ पे ट्रांजिस्टर आप सिग्नल को एम्पलीफाई करना चाहते हो। ओके,
ओ
तो ट्रांजिस्टर इज बेसिकली, अपन पहले से पूछ रहे हो तो बता रहे हैं, ट्रांजिस्टर इज बेसिकली व्हाट? ट्रांजिस्टर
ट्रांसफर ऑफ रेजिस्टेंस।
ट्रांसफर ऑफ रेजिस्टेंस,
यस सर।
ट्रांसफर ऑफ रेजिस्टेंस। ट्रांसफर रेजिस्टेंस का मतलब क्या होता है? आपका इनपुट जो इनपुट जंक्शन है वो आपका फॉरवर्ड बायस है, तो वहाँ पे रेजिस्टेंस कम है। और आपका जो आउटपुट आउटपुट है वहाँ पे आपका रिवर्स बायस है, तो वहाँ रेजिस्टेंस ज़्यादा है। और करंट दोनों में सेम ही है, समझ रहे हो?
यस सर। यस सर।
तो पावर कहाँ ज़्यादा होगा? पावर
हाँ
कहाँ पे?
करंट ज्यादा है।
करंट तो दोनों जगह बराबर ही है, जैसे कॉमन बेस किया, करंट तो बराबर ही है, और रेजिस्टेंस कहाँ पे ज़्यादा है?
फॉरवर्ड में।
फॉरवर्ड में।
रिवर्स में।
तो वही तो रिवर्स में हम कम वोल्टेज सिग्नल लगा के, ट्रांजिस्टर के ऊपर कम सिग्नल लगा के आउटपुट में हम लोग ज्यादा पावर ले सकते हैं। ओके, दैट मींस वी कैन एम्पलीफाई द सिग्नल बाय ट्रांसफर ऑफ रेजिस्टेंस। ओके, वही मैं भी डिस्कस करने वाला था। ओके, ट्रांसफर ऑफ रेजिस्टेंस, तो इसी का पर्पज है, क्योंकि करंट तो सेम फ्लो कर रहा है, बट आपका करंट का रेजिस्टेंस चेंज हो जा रहा है, एक जगह कम है एक जगह ज्यादा है। ओके, सो आईवी भी बढ़ गया, आईवी बढ़ गया। हाँ बोलो।
यस यस अंडरस्टैंड।
Okay, so well, I'll discuss amplifier. हाँ बोलो।
At output in reverse bias current is high na sir?
Reverse bias current cannot be high. IC in the device, IC is almost equal to IE. Okay,
Okay.
but reverse bias resistance is more, and here and forward bias resistance is less. So current is passing, same current is passing through less resistance, and same current is passing through high resistance at the collector base junction. Okay. So let me discuss now the आउटपुट कैरेक्टरिस्टिक्स। तो आउटपुट कैरेक्टरिस्टिक्स क्या होते हैं बिटवीन आईसी एंड, और क्या होता है, वीसीबी। ओके, कीपिंग व्हाट?
IE constant.
IE constant. So let me first keep IE constant. Okay, so let me say first is IE 0. IE 0 है, तब आप वीसीबी बढ़ा रहे हो तो आपको एक करंट मिलेगा। ओके, इस करंट को क्या बोलते हैं? मेरे पास जंक्शन है एन पी एन, अब मैं यहाँ पे रिवर्स बायस लगा रहा हूँ, ये रिवर्स बायस लगा रहा हूँ, और यहाँ पे मैं कुछ भी फॉरवर्ड बायस नहीं लगा रहा हूँ, तब भी यहाँ पे करंट फ्लो कर रहा है। उस करंट को क्या बोलते हैं?
रिवर्स सैचुरेशन करंट।
वेरी गुड, रिवर्स सैचुरेशन। तो अभी जो आईसी मिल रहा है मुझे, वो क्या है बेसिकली? ICBO। ओके, so when I is 0, then in this circuit whatever current is flowing, that is ICBO। तो आपका ICBO करंट फ्लो कर रहा है I इक्वल टू 0 पे। अब आपने यहाँ पे फॉरवर्ड बायस कर दिया, तो यहाँ से भी करंट फ्लो होगा। ओके, तो अब क्या होगा? सपोज आई एम कीपिंग नाउ I इक्वल टू 1 मिली एम्पियर, सो I इक्वल टू 1 मिली एम्पियर। कांस्टेंट, तो मेरा IC कितना होगा बताओ? IC क्या होगा? IC will be almost equal to IE. Yes or no? Okay. अभी ऐसा नहीं समझोगे तुम लोग, चलो ये हो गया मेरा, दिस इज। अब आउटपुट कैरेक्टरिस्टिक्स क्या है? कीपिंग इंक्रीज द वोल्टेज एंड मेजर द IC, कीपिंग दिस करंट कांस्टेंट। अब मैं यहाँ पे वोल्टेज बढ़ा रहा हूँ, यहाँ वोल्टेज बढ़ा के, दिस इज माय फॉरवर्ड बायस, दिस इज माय IE and this is my VBE. Okay, by varying this VBE I can change the current. Yes or no? By changing the VBE I can change this IE current, so I am not changing the current this one. Okay, so again now the current will be sum of this current plus what I'm getting from the base emitter junction, so I call it this IE, say 1 milliampere.
सर मेरा नेटवर्क चला गया था सर, तो सर कैन यू एक्सप्लेन इट वंस मोर?
क्या एक्सप्लेन करना, तुम तो 3-4 बार पहले भी सुन चुके हो इसको, रिवाइज करते नहीं हो तुम। ओके, so now what I'm doing here, I am applying, keeping IE 0, I am applying VCB, then I got this small current IC which is equal to reverse saturation current. Next time what I'm applying now, I'm applying VBE, so I'm getting current here, and this current, when I apply VCB, this all current is collected, so I get constant IC here. Okay, now suppose I'm again increasing this voltage and I'm changing the IE. Okay, so I get now IE, so I get more IC, because IE is always equal to IC, so I'll get more IC here. Say this is IE equals to, keeping IE equals to 2 milliampere. Then I'm again increasing the this voltage, so my IE increasing, so IE increase, so automatically IC will increase. So IC, say if IE is 3 milliampere, okay, then I'm getting IC also 3 milliampere. Okay, so now suppose I'm getting this IE equals to 1 milliampere and I want to make this current 0. So what should I do? अगर मैं VCB को उल्टा कर दूं, अभी तो मैं जो भी whatever charge carriers are coming, I am collecting the charge carrier to the VCB. If I apply VCB forward bias, if I go in minus, that means what will happen? I will do repel. Abhi मैं still I'm capturing the electron, okay, holes, whatever. Okay, I'm capturing the thing VCB. Okay, now if I apply this VCB reverse, so I can stop whatever is coming here. I can stop by this applying this reverse voltage here, or this forward voltage here. So what will happen? If I apply negative, I can make this current 0. I can make this current 0. Okay, I can make this current 0. Okay, so this is your output characteristics. Okay, now this portion of the graph is called your active region. Okay, this portion of graph is your saturation region. Okay, and the region beyond here, below this one, okay, this is called your cutoff region. Okay, so cutoff region मतलब क्या है? जो जब only second में reverse saturation current flow हो रहा है, okay, that is called your cutoff region. Now the region where you are getting parallel lines, this is called your active region, and where your current is getting increased, so this region, okay, this region is called your saturation region. Okay, now let me talk about these regions. यहाँ पे क्या हो रहा है? यहाँ पे ये VCB है, ये फॉरवर्ड बायस है कि रिवर्स बायस है? बताओ इस रीजन में, बताओ इस रीजन में क्या, कौन सी बायसिंग है बताओ? ये VCB
रिवर्स बायस,
ये रिवर्स बायस है। वेरी गुड। और जब ये करंट आ रहा है तब आपका फॉरवर्ड जो आपका जो एमीटर बेस जंक्शन है वो क्या है? फॉरवर्ड बायस है कि रिवर्स बायस है? फॉरवर्ड। सो जो ग्राफ मिल रहा है मुझे किस लिए मिल रहे हैं? फॉरवर्ड और रिवर्स के लिए मिल रहे हैं ना? you're applying reverse, you're applying your output, you're applying this reverse bias, and since you're getting IE, that means you're applying forward bias and input resistance. So your forward reverse, you're getting constant current here. So whenever your transistor is in VCB is positive, VC is reverse bias in NPN transistor, because this is NPN transistor, this is a positive value. So when it's positive and VEB also positive, forward bias, reverse bias, then the operation region called active region. Okay. Now, if I VCB become negative, then this will become forward bias because the NPN transistor, NPN. So N should be connected with the positive, not the negative. If you make positive, then it is reverse bias. Now, if you make VCB negative, then this become forward bias. So this region is corresponding to what? Forward bias, forward biasing. So this is your FF biasing. This is your FF biasing, this region. That's why I call it saturation region. This region is your FR biasing. This region is called active region. And the region below cutoff reverse saturation current, this region is called your cutoff region. Okay, we'll talk more about these things. So basically यहाँ पे आपको याद करना है, if this is an NPN transistor, for NPN transistor your VCB should be positive. Okay, of course, if you want to work in active region, for active region, okay, for active region your VCB should be positive and your VBE should be also positive. Okay, so this is make reverse bias at collector in a CB junction. Okay, this makes forward bias at ammeter base junction. तो ये साइन आपको याद रखना है, एक तो पहली चीज है. एनपीएन ट्रांजिस्टर के लिए ये पॉजिटिव हो जाएगा. पीएनपी फॉर पीएनपी ट्रांजिस्टर इट विल बी अपोजिट फॉर पीएनपी. For PNP, if you want to make this reverse bias, you have to connect with minus. So your VCB will become less than 0. That sign you have to remember while applying whether your transistor is active or saturation region when you want to find out. Okay. Now here you see this graph is parallel to this one. So this is your I and this is your V. तो यहाँ पर resistance कितना होगा बताओ? If some component is giving this type of IV characteristics, so what is the resistance? Tell me. For example, if I draw now like this, I is like and V is like here. Okay, जैसे हमने डायोड में किया था, तो डायोड का रेजिस्टेंस कितना था बताओ इसमें? डायोड का रेजिस्टेंस कितना था इसमें? If I say IV, if I want to calculate resistance is what? V by I. Yes or no? And if you're increasing V, I is constant. Okay, or you say this is del V upon del I. तो इस ग्राफ का स्लोप कितना है?
Infinite.
हाँ?
Slope 0 है सर.
Infinite.
Slope 0 है. Slope 0 है किसका? Del I by del V का. So your del I by del V is 0. So del V upon del I कितना हो जाएगा? Infinite. This del I by del V is 0. तो del V by del I कितना हो जाएगा? Infinite. तो अगर कोई आपका ऐसा ग्राफ दे रहा है इस तरह का, that means here resistance is almost very high. So resistance is very high. Okay. Similarly, if you are getting graph like this, so here
0.
del I by del V is how much? 90 degree, 1090, infinite. So del V upon del I कितना आएगा आपका? 0. So when I do diode, I say this diode has a 0 resistance. You make short circuit if you make diode like this or like this. Okay, even though we increase the voltage, there's no voltage, there's a current is increasing without increasing the voltage. Here current is constant. Even if you're increasing V, current is not changing. So this kind of region, okay. So whenever I apply this forward biasing and this type of biasing, okay, at the output junction, the resistance is very high. Okay, and this resistance, how to write? So this resistance is given by, we denote this resistance by, let's give me 1 minute. Okay, so or you want to write this common base junction, so the output resistance, okay, in common base junction, okay, or collector base पे तो OCB, you can write this one, and that is given by your delta VCB upon delta IC keeping what? Keeping IE constant. Keeping IE constant. And this resistance is generally in mega ohm. Exact value I don't remember. I'll tell you later. Okay. This resistance is generally in mega ohm region. And similarly, if I take my forward characteristics, input characteristics. If I take input characteristics, this one, IE versus VBE, this graph is like this. Okay. And here you have resistance. Okay. Input resistance. If I take input resistance, so this is output resistance. This is if I take input resistance in common base. Okay. So I will at RIB. So RIB will be what? Your delta IE upon delta VB, keeping VCB constant. Okay. And this is called in ohm. This is ohms. This is in ohms. हाँ बोलिए. Delta VB.
delta VB.
Delta VB upon delta IE. Okay. This is in your ohms, if you ohms. So at the input you have a low resistance, at the output you have high resistance. That is called transfer resistance, and that is the mechanism of transistor by which it amplify the signal. Okay. When we learn the amplification, that time I will tell you again how exactly this amplification is happening. So I'm stopping here now. Okay. So tomorrow we'll do this common emitter configuration and we'll do problems. अभी question तो पूछो कोई. If you doubt, we have 5 minutes. Okay. तो कल इसको रिवाइज करके आना. एक चीज तो जो 4 तरह की बाइसिंग है और किस बाइसिंग में कौन कौन सा रीजन होता है. You just go through that one. Okay. And then you try to understand that how to plot input characteristics and output characteristics, whatever I told you. Okay. Try to read from your material, whatever material you given. Okay. And if you're in doubt, you ask me tomorrow.
Sir,
yes.
how many classes will take this chapter, sir?
It will take 6 to 7 classes.
Okay.
Okay. So transistor का जो problems है, that is very simple. Okay. Only just you have to understand a few things. Okay. That I already told in this common base. I will tell again in common emitter that आपका जो VB है, that is 0.7, and VCB is positive for NPN transistor and your VCB is negative for PNP transistor. बस ये दो बातें याद रखनी है. उसके बाद आपका पूरा यही बेसिक है. इसी से आपका सारे क्वेश्चन हो जाएंगे सारे. Okay. I will solve the problems. We'll see this one. Okay. Thank you.
Thank you, sir.
हाँ बोलिए.
सर ये वाले चैप्टर है ना जो ट्रांजिस्टर वाला,
हाँ
इसके नेट के PYQs नहीं है बुकलेट में.
हाँ अभी सॉफ्ट कॉपी दे देंगे आपको इसकी. हमने बना दिया, हमने डाल दिया, हमने भी.
ठीक है सर.
कर देंगे. Any other question? Anjana? Lakshmi, Sian?
Yes, sir.
Any question?
No, sir.
Thank you. So we have 5 minutes more. If you want any question, you can ask. Okay.